Hello, everybody. My name is Tomislav, and I'm together with Srdja here. We are developers from Nordeus, a Belgrade-based company, and we have offices around the world in Dublin, London, San Francisco, and Skopje. We are the developer of Top 11, an MMO football management game. And today I would like to talk about some problems that I think we all have. We will tell you a war story from the trenches of the Top 11 product development, where we had big problems with scene loading times. Also, we had problems with draw calls. Everybody has problems with draw calls on mobile. Then we will share some ideas how you can improve static batching in Unity with tiling. And we will share our own technique that we like to call poor man's instancing. So in our case, we have Top 11. It is a game about football, or soccer for those three guys that are from the other continent. So you become a manager and you battle other players around the world. If you like football, you probably can tell me who this face on the picture is. This is Jose Mourinho. And as football is played in every country, so is our game. We have even had logins from Antarctica. We had an active player there. So why am I telling all of this if this is a talk about mobile optimizations? Well, having success in the emerging markets and being a mature product leads to the fact that we have 25% of users that have really, really old phones that have terrible performance. Which means that we have to be careful with those users. Organic growth and availability of our product are big drivers for Top 11. And if you're not available on those low-end devices, then you will have lower KPIs. So we have been around for 5 years. And 3 years ago, we started switching the company over to Unity. At one point came the time to update the Top 11. We wanted to improve gameplay and to improve visual quality. And this was meant to be a big update. And besides improving players' experience, we also wanted to unify the code base because we had 3 teams all working on the same features over and over again. We had the Flash team, iOS team, and Android team. And Top 11 is a GUI-heavy game. And especially from our own Android team's experience, we know how the mobile market is fragmented. We have different screens, different resolutions, different DPIs. And that's why we wanted to create our own UI system that would help improve the production time of the UI and that would help improve the quality of the UI in our game. This was before the 4.6 UI, but we chose Unity anyways. We chose Unity because it would help us definitely with the first problem. It would make us help to unify the code base because Unity is a cross-platform engine. But most importantly, Unity is a flexible tool. Like John said today in the keynote, Unity is a really flexible tool. We actually started transitioning to Unity 3 years ago, and now we are a company that's fully Unity. Last year, we had our UI framework implemented. Philosophically, it is similar to the Unity's new UI system. But coming from the Flash programming background, we expanded it with some concepts like groups and layouts. And here you can see it in action. We have 2 different screens with 2 different DPIs. And everything is automatically laid out. You create one UI on one scene, and everything works everywhere. We started prototyping our gameplay from the most complex scene, the squad scene. You have many players on a squad in football. You have 11 players on the pitch, but many more in the substitutions. And when you put all those players on the pitch, when you put all these players in this list, when you add all data for every player, and everything has to be automatically laid out, then you end up with 4,000 game objects on the scene. I'm really trying to justify myself here because having 4,000 game objects sounds a lot for something that should be on the UI, but we really couldn't go below that number. We really had to have a lot of game objects. We created our first prototype, and I'm going to show you an early alpha build of Top 11 at that time. This was the big problem that we had. The scene loading time was terrible. It took 7 seconds to load this scene. We didn't know what the problem was. We had a hunch that it had something to do with the fact that we had 4,000 game objects on the scene and 15,000 mono behaviors, but we didn't know what was going on. We started profiling the game extensively. First, we used Unity's profiler. It's a great tool. It's the first tool that you should always use when you start profiling your game. But it only works in development mode, and sometimes you need to have precise measurements during runtime on devices. And the most rudimentary technique that you can use is system.stopwatch and measure milliseconds. And we needed those precise measurements because we were making really, really small improvements in our game, order of magnitude 10 milliseconds at a time. We even had days where the same code would give different results, and it was not the problem in our code, it was the problem because we were measuring things wrong way. As the time went on, we developed our own profiler that's based on system stopwatch, and if you follow this link, you can check it out. This is a technical presentation, but we would like to share some code with you. So I love this community. I've been part of it for 3 years, and I want to give back. So what we discovered is that the first step in loading scenes was too slow. The first step is to deserialize all data from the Unity scene file. And we discovered some weird results in the Unity itself. For example, serialized private fields took much longer to deserialize than public fields. Also, null fields incurred overhead that shouldn't exist there. Also, some hierarchies that are deep took a lot more time to load than hierarchies that were flatter. Also, there were some fixed costs in loading empty scenes. And most of these problems are fixed in Unity 5 and Unity 4.5. I'm just bringing them out here in case you use an older version, so you should definitely upgrade. But as I mentioned before, we are targeting really, really low end of the Android devices, and we wanted to squeeze every bit of performance out of Unity. So we started thinking about implementing our own solution for the scenes. What we did to mitigate this problem is we write our own GUI data to a special binary format. So the pipeline would look like this. You first design and create the UI in the editor using editor tools. When you click build, code for writing and reading from our custom binary format gets automatically generated for every mono behavior that is going to be used in the scene. Then that code is embedded into every mono behavior class that is going to be used. Then we write our super tight scene format and pack the build and run it on a device. When you run it on a device, we don't read from Unity scenes, we read from our customized scenes. This worked kind of better because we were able to remove some data that we didn't need, so we could have this super tightly packed binary format for us. But this was only the first step. We read all the data for the UI, and then you have to instantiate all those objects. And instantiation is a well-known problem. In Unity also, instantiation of new objects is slow. It is slow because you're allocating memory on the heap. And if you delete those objects, then you are deallocating memory from the heap, which can trigger garbage collector, which might further slow down your application. I'm very sure that there are different game object pool implementations, but also here we are sharing our own implementation of game object pools and a generic implementation of a pooling class. So top 11, we knew we were going to have 5,000 game objects max, and at the start of the application, we pre-instantiate 5,000 game objects, and then we reuse them through the entire app. We only take them from the pool, activate them. When we no longer need them, return them to the pool and deactivate them. So far, we have read the scene, instantiated all objects on the scene, and now we have to recreate the transform of hierarchies for all objects to reconstruct the scene as it was in Unity editor before we ran. And when you're reconstructing a hierarchy from code, you can go about two ways. If you're using a simple recursive algorithm, you're going to end up reconstructing it bottoms up. So for example, the transform number 3 gets attached to the transform number 2, then the entire 2 subtree gets attached to transform number 1. Other way around would be top-down, where you would attach transform number 2 to transform number 1, transform number 3 to transform number 2, and so on. And for the worst case scenario of 1,000 game objects, you need 10 seconds to recreate the hierarchy. How long do you think it needs to do it top-down? This was very surprising for us. First time we got to this point, we recreated the entire hierarchy. And guess which way we did it? We did it bottoms up. And we actually made the application slower instead of making it faster. I don't know why this happens. Probably there are some matrices and transform recalculations. But I don't know. I avoid reparenting transforms bottoms up from now on. This is the wireframe of the scene that you saw previously. We got to the point where we have reconstructed the entire scene. We read all layouting metadata, and we have the code that is running. And to show anything on the screen, we need to create UI meshes on the fly. If something is moving on the scene or changing in the scene, we are recreating meshes every frame. So you could say that we are procedurally generating meshes from the layouting metadata that we have read so far from the scene. And if you are familiar with the Unity's mesh type, it requires an array. And you need to know the exact number of vertices you want to pass it to the mesh that you want to render. And if you create a new array every time, you are allocating memory on the heap, which is slow, and you're creating garbage, you are triggering the garbage collector, everything gets slowed down furthermore. This is how an array is laid out in the memory. You can notice in the header that we have an encoded size of the array, and then data is following it sequentially. If we only had pointers like we have in C, we could have used pointer arithmetics to reach this header, rewrite it, and effectively resize the array free of charge. You can have pointers in C#. This is my tip for you. You can create smcs.rsp file, write unsafe directive in it, and you can write unsafe code. Here, again, I'm showing our implementation of something that we call a varying list. It's a generic list which exposes the underlying buffer of an array, and you can resize it free of cost. It was super useful for us when we worked with procedurally generated meshes. So to refresh your memory, I'm going to show you with what we started. And the managers were like, we should probably cancel this project. This cannot be done. This takes 7 seconds to load. And this is how it worked. We released the top 11 Unity update in January this year, and so far we have been featured several times on the App Store. Okay, so far we have talked about top 11 as a GUI heavy game, but in this new update we wanted to have a 3D grounds as well. We have fully 3D grounds. It has similar requirements as our UI. We have to be supported on the very low end of Android devices, so we have to take everything into account. Developing in 3D brought a different set of challenges to development, and as we were developing Top 11, we were also developing another game, and we have a Srdja who will share his experiences from this new game to you.
Thank you. Hello, everybody. My name is Srdja, and today I will talk to you about graphical optimization techniques. We started developing our new game a few months before we started working on Top 11, and this game was completely 3D, and it presented a completely different set of challenges. We learned a lot from it, and we wanted to share it with you guys. So, one of the biggest issues that has always plagued us, and I'm sure you have encountered it multiple times as well, are draw calls. Whenever you want to draw an object on the screen, you have to call a bunch of OpenGL functions. They have a CPU overhead. Some of them even have to call the graphics driver, which adds even more additional overhead. This works the same way on both PCs and mobiles, but PCs have much stronger CPUs, so it's not such a big problem on them. But mobiles can get into critical territory if you simply go above a certain draw call limit. For example, some top-end Android flagship devices can go below 60 frames per second from just 150 draw calls. And that's really not that many for many genres of games. If you're trying to develop an open-world game, for example, you will go above that limit easily. You could go 3 times that, and you won't even notice it. Luckily, there are APIs that are currently being developed that can help with that problem. There is Metal for iOS, OpenGL Android extension pack for Android, and Vulkan, which is cross-platform. Only Metal is somewhat widespread enough to be used, and it's also supported in Unity, and you should always use it if you have the chance. But what if you're targeting older iOS devices or any of the Android devices? There's a lot of old devices out there which will never support these APIs, and it will take a couple of years before they die off. Until then, we have to solve the problems of draw calls ourselves. And let me just present the scenario that we had in our new game. We had an absolutely huge scene. It was at least 5 by 5 kilometers in size. It had huge open spaces, and it had large draw distances. It had a lot of vertices, and it had a lot of objects. It also had a fast-moving and fast-rotating camera. All of these factors combined together to create a lot of draw calls. I mentioned the fast-moving camera. You might not think that's an actual problem, but we were developing in Unity 4. And there's a great technique to reduce the number of draw calls called static batching. It's enabled by default, and you should always use it, except when you have a fast-moving camera. The way it works with the fast-moving camera is that it can actually reduce your performance drastically, and that happened to us. Luckily, this has been fixed in Unity 5, so if you're using that, that's great. If you're still on 4, you should check if that's happening to you as well. And I mentioned static batching, and that's the first thing I will talk to you today because it can reduce the number of draw calls that you have by the most. When you have a bunch of small static objects that share the same material, you can combine them together into one big object, which can be drawn with just a single draw call, compared to multiple draw calls the smaller objects would take. Having a shared material is a prerequisite. So you want to have as little materials as possible on the scene and to share them as much as you can. There's another great technique that comes into play here called atlasing. Atlasing is the process that you can see on this picture. You take a bunch of textures and you combine it into one big texture called an atlas. That way you can have a single material that has the atlas as the texture, and all of the objects that read from those separate textures are now reading from that single texture and share a single material. There's a great white paper on this subject from NVIDIA called Improved Batching Using Texture Atlases. If you want to know more, you should read it. And we had large urban environments. To make them look good, you have to use texture tiling extensively. Tiling is a technique where you repeat a texture several times side by side on an object. This is done because a lot of objects cover wide areas, and creating a texture for the whole object would consume either a lot of memory, or the texture would have to be a really low resolution, which would make it pointless. With tiling, you can create a smaller texture and repeat it on the surface. This works great for surfaces that repeat in real life as well, such as asphalt or bricks on a wall. And well, here's where we got to a problem. First, we had the performance issue from the fast-moving camera, and then tiling does not work in combination with static batching and atlasing in Unity. We needed to use it to make our environments look good, so we decided to make our own twist on static batching. And the first problem that we wanted to solve is the tiling. There are two approaches to this. The first one is by adding additional vertices to the object. As you can see on this picture, there are 3 quads. Each of them is unwrapped from 0 to 1 in UV space, and effectively the texture would be tiled 3 times. This actually works pretty well, but it has a lot of downsides. First of all, you have to add those additional vertices, and it usually has to be done by artists. Secondly, all those additional vertices can put you way, way above your vertex limit. For us, it would absolutely double the number of vertices that we had, which was simply not acceptable. And thirdly, if you have large irregular shapes, this would be hard to do. Due to these downsides, we didn't want to do it this way. We wanted to do it the other way, and that's doing it in the fragment shader. And this is actually how Unity does it when you don't have atlases in the picture. We now have one big quad. It doesn't have any additional vertices, but the UV coordinates are repeating 3 times, and the texture will be tiled 3 times. If you remember Unity's material inspector, you will know about 2 parameters in there. They're called tiling and offset. They're used to control these values, and they work great without atlasing. But in atlases, you have a bunch of different textures and a bunch of different objects that read from those textures, and they need to be tiled differently. Since those parameters are unique per material, we couldn't use them. You'd have to use parameters that are per object or per texture. And that's the first issue that we have to solve. This is how the process should look. First of all, you would have a script that would batch all the meshes. And lastly, you would have a shader that would draw that mesh by reading the custom tiling data. The middle step is the problem, how to pass the tiling data to the shader. And there's a pretty cool way to do this. It's called vertex attributes. All of the vertices have some additional information linked to them. One of the most basic ones is called vertex position. That's pretty much the position of the vertex in the world space. So, important thing that you need to know about vertex attributes, and the most cool thing about them, is that you can use any vertex attribute for any purpose whatsoever. Just because one of the vertex attributes is named vertex color does not mean you actually have to store colors in them. So we needed to choose an attribute that we would use to store that tiling data, and there are a bunch of them to choose from. The first one is vertex colors. It's usually used to make the scene look more diverse. The second one is vertex normals. It's usually used for lighting. And the third one is the UV channels. There's actually multiple UV channels. If you're using Unity 4, you have only 2, and they're usually used for texture mapping and light mapping, and you want to keep it that way. If you're using Unity 5, however, you have 2 additional ones that you can use. And there are tangents. Tangents are usually used for normal mapping techniques, but none of the objects that we wanted to batch had any tangents. So in our case, we decided to put all the data into tangents. And that is our missing step. We first batch all the meshes. Then, for each object, we put that custom tiling data into the tangents of its vertices. And lastly, the shader reads the tiling data and displays the mesh. And at this point, everything worked and looked good, and we thought we solved all of our problems. But then something happened. Well, our textures could be looked from very far and very near. If you have textures like that, you absolutely need to use MIP maps to make them look good. And when we turned on the MIP maps for our atlas, this happened. So the picture on the left is the asphalt, how it should look, and the picture on the right is how it actually looked after turning on the MIP maps. Notice the diagonal line in the red square that appeared. And sorry for the potato quality. This line is literally 1 pixel wide, so it had to be magnified a lot. What happened is that on the every edge of a tile, when we ended one tile and started another, this kind of lines appeared. It took us a lot of effort to discover what was happening. And after a lot of research, we discovered that at those exact points, a lower MIP map level was read from. But there are two problems now. First of all, why does the lower map level look like this? It should look somewhat close enough to the asphalt as to not be noticeable. And secondly, why is it even red when the pixels left and right were reading from the correct MIP level? Well, here's the answer to the first problem. On the left, you can see the picture of the texture, how it looks normally. And on the right, you can see it how it looks on the lowest MIP level. Notice how the texture on the left has nice primary colors, and texture on the right is simply brown. Well, the problem is that when downsizing the texture to lower MIP levels, all those colors combine together to produce this brownish color, which does not fit with any of them. And that's why the line appeared. We were reading from very low MIP level. And now, why were we actually reading from that MIP level? That's a bit more difficult, but this is the reason. This is the correct situation. You have a texture that's tiled in the atlas, and the blue pixel is the previously red pixel. The yellow pixel is the currently red pixel, and they're right next to each other on the screen. Notice how the difference is very, very small. It's 0.01. And that's great. But what happens in the situation when we have the problem? The previously red pixel is on the very right edge of the texture. The currently red pixel is on the very left edge. The difference in UV coordinates is now very large. It's 0.3. This is a problem because the GPU uses these numbers to determine what MIP level to use. If this number is small, the texture is very near to you, and the lower MIP level will be used. If this number is large, like in this case, that means the texture is very far from you, and a much higher MIP level will be used. And that's what we needed to solve. Luckily, a lot of people actually developed techniques for static batching, atlasing, and tiling on PC about 10 years ago, and they encountered this exact same issue. And something was developed for PCs. There is a way to manually specify what those distances are so we can calculate them correctly ourselves and then tell the GPU to use those distances instead of the ones it calculates. And this is where I have some good news and some bad news. The good news is that there is an OpenGL extension that allows you to do this. It's called Shader Texture Level of Detail. The bad news is that it's an OpenGL extension, and I'm sure you all probably know how that works. Not all manufacturers have to support it, and even if they do, they don't actually have to support it in the same way. From our testing, it was completely supported and working on modern iOS devices, but on the Android side, it was only supported on Mali GPUs, and only on some of them, and it was supported. What I mean by that is that it actually reported that it supports the extension, but when we tried using it, it caused weird graphical corruption. Well, this wouldn't do. We simply cannot release a game where every few seconds you would see a line across some texture. And that's when we tried to figure out some solution. We tried a lot of things, and I'll only tell you about a few of them. First of all, we tried to expand the texture that should be tiled to the very edge of the atlas. Notice the red square. That's the original texture, and it's been copied horizontally multiple times to the very edge of the atlas. Why was this done? Well, when you use hardware wrapping, which you will since the texture is spanning the entire atlas, the GPU knows how to calculate those coordinates correctly. But this technique has a lot of downsides. First of all, since the texture is only repeated horizontally on the atlas, you can only repeat it horizontally in your objects. If you wanted to repeat it vertically, you would have to repeat it vertically in the atlas as well. And as you can see, it takes up a lot of space. It makes your atlases bigger, and it consumes more memory. And for those two reasons, we simply couldn't use this technique. Now for the weirdest thing that we have tried. We figured, what if instead of jumping straight from 1 to 0 when we got to the edge of one tile, we did it gradually over the course of an entire tile. So in this picture, the first tile is going from 1 to 0 in UV coordinates, and it's OK. But when we get to the second tile, we start going backwards. So UV is going from 1 to 0. And that would effectively make the texture mirrored. And the third texture is going the right way again, the fourth texture is going backwards, etc., etc. This completely limited the lines, but it caused a huge problem. You see, The human eye can recognize symmetry very well. And that was an issue, because all of the objects that were unwrapped this way look completely uncanny. And this was completely unusable. So we decided to try something much different. What if instead of eliminating the problem, we simply masked it? Look inside the white square, for example. All the textures in there are kind of bluish. When they get downsized for a lower MIP level, they will be combined together and the result will also be bluish. And because of that, those lines will be much, much less visible. We didn't actually think this solution would work, but it did. Almost all of the lines became invisible, completely invisible, or almost completely invisible. And that's the solution we actually went with. This was simply a good enough solution. It was not perfect, but nobody could actually notice the lines. So it's really a question, if nobody can notice them, do we really need to spend more time? Do you need to delay your game just so you can solve the issue only you know about? And this took a lot of effort, but the results were well worth it. First of all, there were much, much, much less draw calls. Because we could even batch tiling objects, we could use them liberally across the entire scene, making the environments look nicer. The reduction in draw calls caused us to easily hit our performance targets, and we went completely under our draw call budget that we could even start adding objects to the scene. The only issue that exists here is the bit of added complexity in the fragment shader, because you need to calculate the UV coordinates manually. But from our testing, that's only about a 5% performance loss, and only if you're completely GPU bound. And at this point, we solved our problem with static objects. All of them took only 40 draw calls on the scene, and everything was great. But there's another category of objects that we haven't even gotten to, and they can add a lot more draw calls than static objects can. And those are objects that are moving. This picture illustrates the scenario that we had in our game. There are a bunch of cars on that picture. All of them have at least 4 wheels, and all of those wheels need to be turning for this scene not to look uncanny. And that added a huge amount of draw calls, and it needed to be solved. For an even more extreme example, here's a truck. It has at least 12 visible wheels, and since we want to target a wide range of devices, we wanted to stay below 150 draw calls. This thing alone would take up 10% of that budget when it appeared. So we started looking for solutions to this. We cannot use static batching because the objects are moving. Maybe you could use Unity's dynamic batching, and that's what we first tried, but it didn't work. The issue is that Unity's dynamic batching has a limit to the number of vertices that it can batch. This is done for performance considerations. You also cannot choose what objects will be batched and what won't. And those 2 factors simply didn't work for us. But there is a great technique that can help us with this. It's supported in OpenGLS 3.0, and it's called instancing. Instancing is the process where you take a single mesh and render multiple copies of it with different parameters such as position and rotation in one draw call. Unfortunately, it's not supported in OpenGLS 2.0, and those devices are still 60–70% of the market. And they usually have much worse performance, and they need this optimization much more. So we wanted to solve this. We started thinking, what if we could replicate something like this in OpenGLS 2.0? And that's what Tomislav called Pullman's instancing. We first need to understand how this works. Well, first you have instance ID. This is a parameter that you get in your vertex shader. It indicates what object are you currently drawing. For example, if you're drawing wheel number 1 or wheel number 2 or wheel number 3. The second one is an OpenGL API call called drawElementsInstance. This takes a mesh, the number of copies of the mesh, and all the transform matrices, different parameters, etc., and draws them in a single draw call. So how can we replicate this? Instance IDs are really easy. We can use the same technique that we used on static batching. That is, put those instance IDs into tangents. DrawElementsInstance is a bit harder because there's nothing in OpenGLS 2.0 that can render multiple objects in a single draw call, so we created a custom mesh. And lastly, we needed a shader that would take that custom mesh, read from the tangents, get the transformation matrices, and apply them correctly. And here's how it works. We have a wheel. That's the original mesh. We want to draw a car that has 4 wheels. So we create 4 copies of the wheel and batch them together into a single mesh. This mesh now has those 4 copies. And all of the tangent IDs are baked into the individual wheels that are in that mesh. This is only done once when we want to batch the objects. After we have done this, every frame, we send the transformation matrices to the shader, and we draw the mesh with that shader. And the shader takes each vertex, reads the ID from the vertex, and applies the correct transformation matrix. And unlike static batching, this actually worked from the first try, and it worked really, really, really well. The only 2 issues are vertex shader complexity, which was only a theoretical issue. We couldn't measure any performance drops. The only realistic issue is the memory that all of those meshes would take. The thing is that you really don't want to use that technique on objects that have multiple tens of thousands of vertices. You want to use it on objects that have thousands of vertices. And in that case, even the lowest end phones with 256 megabytes of RAM could fit that into memory. You probably memorized this link by now, but this technique is also shared. You have the shader, you have the code, so feel free to use it. And for the last topic that I want to talk about, let's return to the first picture that I started with. We absolutely love foliage, and we especially love trees, as you can see from this picture. There are somewhere around 300 to 500 trees on this picture alone, and drawing them one by one would consume way too many draw calls and drop your performance considerably. So we needed a way to batch them. We wanted to use 3D trees at first, but we couldn't do that because for 3D trees to look good, we needed a lot of additional vertices. And we simply didn't have the budget. So we went with the old tried and true technique called billboarding. Billboarding is a technique where you take a quad, you put a texture on it, and you always rotate the quad to look towards the camera. It's pretty much a sprite that always looks towards the observer. And since we have done that, we cannot use static batching. Those quads need to be rotated every frame. But maybe we could use something similar to instancing. The only issue with that is that there are so many trees. And passing those 500 transformation matrices to the shader would cost a lot of time. Way too much. It would drop your performance considerably. So we couldn't do that. But then it got us thinking. Those transformation matrices are really easy to construct. You just need to know the position of the tree and the position and orientation of the camera. And you can get the position and orientation of the camera inside of the shader. So what we did is this. We first batched all of those trees together. But we did it in a special way. We again needed to store some additional data into vertex attributes. First of all, we needed the pivot point. That is the lowest middle point of the billboard, the point around which the billboard will rotate. We didn't use colors for billboards, so we decided to put pivot inside colors. But here is where you need to be a little bit careful. Even though you can put any kind of information to any vertex attributes, not all of them have the same precision. Colors only need 8 bits to represent themselves. So the color vertex attribute is only 8 bits, and that's really not enough precision for position. So we stored it in normals. I mentioned tangents and normals, but if you have ever used them in a shader, you will know that they're actually normalized before they get to your shader code. It took us quite a bit of digging to figure out how to reverse this effect, but we managed to find a compiler directive called GLSL no auto normalization, which you can use to make it so those tangents and normals are not normalized. And well, besides the pivot, we also needed to know the vertex positions. In the vertex positions, we stored offsets of those points from the pivot to allow for easier rotation. And lastly, when we got to the vertex shader, we simply took the position orientation of the camera, we took the current vertex, its pivot, and created a rotation matrix that rotates this billboard. This actually sounds kind of difficult, but it really isn't. You can find the code for this shader on this link, and just look at it. It will seem really easy once you read it through once. The only two issues that exist here are vertex shader complexity, which is not trivial this time because you do have to construct those matrices inside of the shader, but the performance loss is negligible. And the bigger issue that exists with this batching technique and pretty much all of the batching techniques is that they usually don't work with transparency very well because the sorting order can get messed up. But they work great with opaque and cutout objects. And well, those were all the techniques that I wanted to share with you today. And I hope you will find them useful and you'll be able to use them in your game. And I would like to call Tomislav back to the stage so he can conclude this talk.
So today we told you a story about how we almost never released the top 11 update, but we saved it after we learned how to properly measure the problem. And Srdja then told you how you can improve some features of Unity, like static batching, dynamic batching, and billboarding. And the key takeaway would be that there is no silver bullet. These optimizations work very well for our use cases. I hope that we have been very useful to you and that we gave you some cool information. Now, I would like to conclude this talk, and you can ask anything you want right now. Question over there.
Hello. Did you have any differences between instance speed on Android and iOS? Because we have like a lot of problems with Android instancing, but iOS fast.
Instancing or object instantiation?
Object instantiation. No, sorry. When you have like getting instancing objects to scene, Unity.
Oh. I'm not really sure. Is there any big difference between Android or iOS? But the most problems we had were on Android. And we were optimizing for Android devices more than iOS devices.
Hello, I'm new to this technology called, or this way of working called pooling. And I was wondering if there is also an overhead if you instantiate components. Because if you have a GUI, then obviously on all of the game objects there are individual components. And if you recreate from a pool of already instantiated game objects, you would have to add all those components. Does that make any problem?
I know that we reset the entire state of the game object. We destroy all components, and I'm not sure what we do with the components.
Yes, actually, mono behaviors are much slower to instantiate than game objects, so you really should pull them before you start pulling game objects.
But what is then, if you have more or less the whole hierarchy instantiated with all the components on it, you more or less already have the whole scene. Is that right?
Yes.
Never mind.
No.
Going to ask you afterwards. Might be too complicated.
Of course, we can talk after. We will be at the speakers booth.
And if I may, another question. How did you solve this problem with transparency sorting and all the tree billboards in the end?
We didn't. We actually used cutout shaders for the trees because they looked perfectly fine. We thought they wouldn't, but when we tried them, they looked great.
I think they were usually in the background and they didn't take up much screen space and it never became an issue.
Hello, I'm new to the instancing that you were talking about, but what if I had an object, for instance, that's got like 1,000 vertices that I'm animating in a shader? Would that be an appropriate technique to use to instance that tile the way that you presented?
It depends. How are you exactly animating it?
Just through a shader that's calculating, Gestirner waves on the actual tile.
That should probably work, but you have to consider that the same shader will render multiple copies of that mesh. So if you can figure out how to write that shader to work in that case, you can use it.
Okay, thank you.
I think you can modify our technique, check out the shader. Of course, you should check out our shader, and I think you can modify it to suit your needs.
We found out that some Android devices don't actually support halves, only fixed, even in vertex shaders. How did you manage to fix tiling on such tilings?
We actually never encountered those devices, I don't think. Which devices were they?
I can give you a list, I think.
Just one would be fine.
I don't know it from head, but I think it's one LG Alcatel or something.
Please come to the booth later so we can discuss this.
Thank you.
Hello. You note that the color attribute is only 3 bytes in size, while the tangents are 12 bytes in size. So I wonder, for example, for atlasing, why do you use tangents instead of color? I think it's an opportunity to save 9 bytes of data for every vertex.
Yes, that opportunity exists, but we actually already used the colors. We had a lot of the same objects on the scene, and we wanted to make them look diverse, so we simply vertex colored them differently.
That's clear.
But yeah, you should use the lowest precision that you can get away with.
Hello. You say that creating a hierarchy bottom-up is way slower than top-down. Did you ever figure out why that is?
We actually wanted to ask the Unity guys after this.
And did they tell you anything?
No, we still have to ask them.
All right.
But we think that some transformation matrices are being recalculated.
Yeah.
And I just want to mention something that Tomislav didn't. That was the example with 1,000 game objects. The time doesn't rise linearly. When we tried it with 3,000 game objects, my phone actually overheated after 20 minutes of that.
Tiling, that there was some bleeding and pixel bleeding in the textures? Or did you?
We actually didn't, but if you have such an issue, you can bleed the textures themselves inside the atlas. So they are a few pixels wider than they
so
usually
just
are.
leave a bit of space.
Yeah. But there's an issue that we did encounter with UV coordinates. They seem to have really low precision, and we had some parts that were unwrapped into UV coordinates 100 or something like that, and they looked completely wrong. So you should be mindful of the precision of UV coordinates on iOS. That might actually be our issue.
Okay, thank you very much.
We have a question over there.
And it's not an actual question, but I'd just like to follow up on the transform order, bottom up and top down thing. I'm pretty sure there already is a blog post by the Unity guys explaining why there's a huge difference in that, and I'm not quite sure. You might look it up yourself, but I think it might have something to do with applying the local transformations. So if you make it in one way, you have to update many more transforms than when you make it the other way for local transforms and like position and rotation and stuff. But I'm not quite sure. You can look it up. I'm pretty sure that there already is a Unity blog post about that topic.
That makes a lot of sense, and that what we actually thought happens. Just we're not sure, but I think you are correct. Thank you very much for the great questions. This was a great discussion, and see you later at the speaker's corner.